So sorry for the interruption here. Network is an issue. So can anyone reply me? Any difficulty in audio and video now? Both audio video is clear. Okay, thank you. So I have started with refrigeration system. So you can recall both refrigeration by vapor system as well as vapor absorption systems. For vapor compression system, we need to run a compressor. So in that compressor, we need to use the electrical power. So that electrical power can be also used from solar energy, one of the method, or in the absorber type of refrigeration system or the vapor absorption system. One can directly go for solar energy, direct application of heat. So in the generator of that vapor absorption system, one can utilize the solar energy or the heat energy directly to exchange the heat with refrigeration system or the cooling system. So one can recall vapor absorption parts here. See, if any disturbance is there in between, just unmute one of you and tell me, or else you can just message me in a WhatsApp. Okay. If any disturbance or the difficulty is there in the presentation. So coming to the system, in vapor absorption system, we will be having the different parts similar to vapor compression system. So only compressor is replaced with a heat exchanger or the generator, or we also call it as an absorber. So here we'll recall the common parts. First is the evaporator. So whenever we talk about refrigeration system, the first important part is the evaporator, from which we are going to extract the heat from the cooling space, and the refrigerant which is flowing inside that evaporator will be heated, or it will convert from liquid to vapor state. So in this example, I have taken ammonia and water mixture, or you can call it as NH3H2O mixture for refrigeration system. By using this ammonia, one can go below 0 degrees centigrade. So that is the advantage of this refrigeration system. Another example is for space cooling, we can go for lithium bromide and water mixture. So there lithium bromide will be acting as an absorber, and water will be the refrigerant. And in this refrigeration system as shown, ammonia will be acting like a refrigerant and water will be acting like an absorber. So coming to the parts, so evaporator, as I told, this evaporator will be placed in the cooling space. This will be extracting the heat from the cooling space. So whatever the heat should be removed from the cooling space, that will be removed from this evaporator. And in the evaporator, as the name indicates, the liquid refrigerant like ammonia will be converted into vapor form. That will be supplied to absorber part. Now in the absorber, what happens is this ammonia and water will be added or the mixed together. So water will be absorbing the ammonia vapors, and after converting that into liquid form, so that liquid form will be pumped to the heat exchanger. Through heat exchanger, it will be again supplied to the generator. So in the generator, or before entering to generator, this regenerator of the heat exchanger will help us to extract some waste energy from the regenerator to the liquid ammonia and water mixture. Then that will be supplied to the generator. So in the generator, you can see, okay. So for the another elective, you can attend the regular classes. Later I will share the video, or once again we can conduct the class in the next week. Those who have another elective, you can join the other class also. Now coming to the generator part. So in the generator, whatever the mixture we have supplied, like refrigerant and the water mixture, that is supplied in the generator, and the heat is, so this is like a compressor. Entire unit is acting as a compressor with vapor absorption. So whatever the vapor is absorbed in separate, means we are going to separate refrigerant and the liquid which is going to absorb. So this heat is supplied for the required vaporizing or evaporating point of ammonia after heat is deployed. So generally for refrigeration systems, we need constant collectors or very high efficient flat bed collectors. So these flat collectors or the solar collectors like concentrated collectors will be absorbing the heat, and any of the liquid like oil or something can exchange the heat with this absorbed liquid. By this, what we are going to do is the heat between the solar flat plate collector or the solar collector with the refrigerant mixture, and only refrigerant vapors, because as I told, once it crosses the vaporizing point for refrigerant, the refrigerant vapors will come out to this rectifier or the filter like device. So only vapors of refrigerant will be passed through the rectifier. Water vapors which are condensed here will be coming back to the generator. So whatever heat is again passed through this regenerator, the recollected water from the rectifier will coming back to the regenerator, and with the expansion valve to cool it, it will again come back to this absorbing chamber. Okay, so this is the water cycle. Water will be moving, or the absorbing liquid will be moving from the absorbing chamber to the pump, regenerator, then generator, and again it will come back to the absorber through rectifier, regenerator, and the expansion valve. So this expansion valve will help us to reduce the extra heat what is present in the water. So it should be in a liquid state to absorb the ammonia or the refrigerant. So that is the cycle here for the water. For the ammonia, if you see, the liquid ammonia and water will be passing through the pump, regenerator, generator, rectifier. Then again it will flow back to the refrigerating cycle. So in the condenser, if you see, whatever the heat or the vapor of the ammonia was present, so that will be taken out towards warm environment, external environment. Then after condensing, the liquid ammonia particle will be passed through the expansion valve. So in the expansion valve, we are going to reduce the pressure. By sudden reduction in the pressure, temperature also decreases, and it will come out from this expansion valve at very less temperature and the pressure. And that liquid cold ammonia is passed to the evaporator again. Like this, the cycle will continue. So you can just remember in the solar refrigeration part, we can have the absorption chamber connected with the solar collector, and from the absorber unit, the ammonia vapors are collected back by separating the absorbed liquid, and only the refrigerant is separated and again taken back to the condenser. And from the condenser to evaporator, we need an expansion valve to reduce the pressure and temperature. So until this audio was clear, the presentation and audio. Okay, I'll explain one more similar cycle with space cooling, where the temperature levels are very low for the cooling purpose. So that is one more space cooling application is this solar refrigeration or the space cooling. So this is actually not used for refrigeration. This is used for only the cooling purpose of the space cooling, big space cooling we are using. Here you can just observe, here in this cycle, water is acting like a refrigerant. Water is acting like a refrigerant. Lithium bromide liquid is acting like an absorber. So by this cycle, we need to absorb the water again and again in the cycle, and we need to separate the water with the lithium bromide in the generator. So in this cycle, one should understand both the chemicals which we are going to select, like a refrigerant or the absorber, both can mix easily and can separate easily at high temperatures. But chemically, it should be very stable for given range of temperatures. It should not mix and it should not become any other chemical reactions. So that care should be taken. So observing that, they have chosen lithium bromide and water for the cooling the spaces. And for this, the temperature is just below the atmospheric temperature, not going up to 0 degrees centigrade, because as water we are using, whatever the cycle they have considered here for the expansion or the generator, the temperatures are very less. So as you can observe in the collector, the temperature is 100 degrees centigrade to separate water, because water can evaporate above 100 degrees centigrade in atmospheric pressure. And water cooling temperature, if you see, for this cooling space, it is up to 15 degrees centigrade, only up to that. So such cycles can be used as a air conditioning systems. So these systems are also available in India also. And one best part of this refrigeration or the space cooling systems are, whenever in the summer season or the very hot conditions only, we need the refrigeration or the cooling systems. So keeping in mind that only in summer season we want the cooling applications. So whenever summer seasons are there, the hot sun or the clear sun is available for the maximum radiation on the flat plate collectors or the solar collectors. Also, in same conditions, we also need more cooling. So these systems will have the more advantage because of its working seasons. So these systems can work in summer season where we need very hot conditions or cooling conditions in the given spaces. So this is one of the advantage. Now coming back to the cycle, again you can recall the parts of refrigeration system. So in the vapor absorption refrigeration system, again I will start with the evaporator as a part. So this evaporator part will be kept in the cooling space where the cooling should be done, or the heat from the cooling space can be extracted. And after extracting this heat from the evaporator, the refrigerant will move to the absorber unit. In this absorber unit, we have a absorber like a heat exchanger, then a pump to pump the absorbed liquid, the mixture of the liquid, to the regenerator and the generator. And from the generator, again we are going to separate this water and lithium bromide. And this water vapors will come out from the generator or the absorber component. And lithium bromide, which are having high evaporating temperatures, so these will be in liquid state and again taken back through the rectifier or directly to the regenerator through expansion valve. And this liquid condition lithium bromide will be again collected back in the absorber heat exchanger. So this is about absorber part. From the absorber, the vapors of water at very high temperatures taken to the condenser. So this condenser will be kept outside to extract the heat and condense back this high temperature water into minimum temperature water condensate. So this heat will be taken outside the building, and once this is taken out, you have to supply a expansion valve or a small diameter pipe for a long length, so that the maximum pressure reduction can happen and maximum temperature reduction can happen through the expansion valve, and again it will come back to the evaporator. So this is the cycle of the refrigeration unit or the space cooling system. Now coming to the working of this. So in the evaporator, the heat is extracted by the water in the liquid form. So after extracting the heat, so heat may be up to 50 degrees centigrade in the given cooling space. So water may be just hot water, not in vapor state. So after extracting the heat, that water liquid form can be extracted to the absorber. So in the absorber, what will happen? Liquid lithium bromide as well as water, both will be mixed here. So temperature may be up to 30 or 50. So after extracting this water vapor, liquid hot water form, the temperature may be up to 30 degrees centigrade. And to cool these liquids, we have cooling water here, or in the absorber, the temperature may be reduced up to 30 degrees centigrade. So once this is done, the mixture of this water and lithium bromide, both can be pumped to the generator bed. And while going to generator, some heat can be, or the waste heat from the lithium bromide liquid from the generator can be extracted in this regenerator. And in the generator or the heat separator, if you see, the solar collector heat can be extracted, and water vapors, once it crosses 100 degrees centigrade, the water vapors can be supplied to the condenser bed. And lithium bromide remaining liquid can be taken out and it can be supplied again back to the absorber. Okay, this is a cycle of lithium bromide. This will be inside the absorber part only. And water as a refrigerant, it will pass through the condenser back in the vapor state. So again in the condenser, we are going to condense it up to 40 or 50 degrees centigrade. And low temperatures like 10 degree or 15 degree can be achieved by passing through the expansion wall. So here we are going to pass it through a sudden expansion wall or a long small diameter pipe where complete pressure of the refrigerant should reduce to a drastic levels. So by reducing the pressure, temperature also reduces. And this temperature, if you see, 15 degrees centigrade, and after extracting all the heat from the cooling space, after a number of cycles, it is going to extract a large amount of heat. And the heat in the cooling space can be maintained for the given comfort level. And that comfort level can be maintained by using different types of collectors or controlling the temperature of this collector, or else you can control the speed of the pump. You can control the temperature of this cooling space. Okay, all of you understood the refrigeration or cooling application by solar system. So you can remember ammonia and water as a mixture for solar refrigeration. Water and lithium bromide you can remember for the space cooling, because temperature levels are little bit higher, cooling temperatures are little bit higher compared to the ammonia. Will you continue? Okay. So one of the representation with the line diagram they have given refrigeration system. Just you can go through for 1 minute. Solar absorption, air conditioning with I think we'll be working on lithium bromide composition. So again, just you can recall here the difference is solar collectors are collecting the heat, okay, and that oil or the any given liquid will store the heat here. So again, as we discussed earlier, the heat storage can be done by either sensible or the latent heat storage by using raw other materials. And from this storage, because they are using storage, because anytime if you don't want the refrigeration application or the cooling application, we can stop this cycle. Okay, right side cycle can be stopped. But on the left side, the heat storage tank will be continuously absorbing the heat from collectors and it can be stored for long time. So in between, whenever we need refrigeration cycle to run, the same heat which is stored in the storage tank or the sensible storage tank, you can again start the pump or the valve can be open and refrigerant will flow through, or the absorbance absorbed mixture can flow through this generator, pump, heat storage device, and if required, auxiliary heater can also be used. So this is just a different type of cycle to show it in a line diagram. So with auxiliary heater or the generator heat, we are going to separate the refrigerant and the absorbent. So once that is done, the refrigerant will be taken out from the generator. It can pass to the condenser, evaporator. Okay, so like this again the system follow the refrigeration cycle. So below part you can see this is the refrigeration part or the absorber part, below part. At the upper stage you can see after taking the refrigerant, it can be passed through the expansion wall. Okay, here I think after generator, condenser, and between condenser and condenser and evaporator, you can see the expansion wall, EV. Expansion wall is shown at the top. And for condenser, the cold water can be taken, or the cooling water can be taken from the absorber itself, or external cooling system can also be used for the condenser. So this is one of the type of representation. We can represent in this form also. Any one of the sketch you can draw and you can explain solar refrigeration or the solar space cooling. Now we'll come back to the solar pond. This is one of the other application where we are going to extract the high temperature from the solar radiations. So in this left side sketch, you can see a pond. In this pond, the bottom side is insulated, or the side walls are also insulated. And in this solar pond, we are going to maintain 3 zones, or to supply the water with the salt with different concentrations. And as all of you know, if the solar or the salt concentration changes, so if water is having maximum concentration, it is having high density. So we assume that in the third stage, or the very bottom side, the large concentration of the salt is maintained here in the third stage. So that is also shown on the right side sketch here in the graph. Concentration of the salt by weight. Okay, so that concentration percentage, if you see, it is increasing up to 50%. So 50% salt added with the given weight of the water. So that is given in the third stage, where concentration is little bit high. And in the depth level, if you see in the second stage, in depth level also we need to maintain up to 1 meters, not beyond that, because the solar radiations once pass through the solar pond. Okay, these all layers will be having some absorption of the solar radiation. If you go on increasing this depth, what will happen? The solar radiation available at the bottom level, which is more than 1 meter if it is maintained, the radiations availability at the last stage is very difficult. So to have maximum absorption, the depth of these solar ponds is maintained up to 1 meters only. And between 0.4 to 0.8 meters, if you see, or 0.2 to 0.8 meter, if you see, the second stage is there, or the second level is there. So in this in between level, we are going to maintain the salt concentration in between. So water and salt is mixed in very less concentration, like you can see here. It is just below 0.3%, sorry, 30% to up to 15%. Salt is maintained. And at the top level, if you see, top layer, as the salt concentration is very less for the given water mixture, the density will also be less. So for this very low density, what will happen? We are going to maintain the concentration up to 10%. So like this, we are going to maintain the concentration in the different levels, different concentrations. So it will increase from top level to the bottom level. And as the concentration is increasing from top to bottom level, here insulation is also done for the third level and also the walls of this solar pond, so that any heat is extracted for the salt water should not be sent out easily, or it should not be lost by convection or the radiation. So insulation will be done at the wall and bottom of the solar pond. So once the solar radiations are falling on this solar pond, it will be absorbed in first level, second level, and third level. And as the third level is very high concentration is there for the salt, it will absorb maximum heat. Second level, medium concentration, it will absorb medium radiations, the intensity is medium. And the first level, if you see, the solar concentration is maintained very less. So the heat absorbed by this first level will be very less. And you can observe the temperature also. So temperature, if you see at the top, we have written the temperatures in degrees centigrade. First level is maintaining up to 40 degrees centigrade. Medium level or the second level, if you see the concentration temperature is up to 80 degrees centigrade, and as it go beyond, it may up to 90 or 85 can reach 95, 85 degrees centigrade. The temperature can be reached, and this temperature at the bottom level can be used for different applications. So one application, as we told, it can be used for solar refrigeration or space cooling or heating purpose, or also power generation purpose. Okay. So once you remember this graph of temperature versus depth in meters, or concentration of salt by weight with respect to depth, if you remember, one can easily draw the solar pond, and the understanding of the solar pond working also will be easy by this graph. So as the depth increases, we are going to maintain different concentration of the salts, and for different range of salt concentration, the density also changes. So density will be high at bottom, low at the top. So as density is high, the density of temperature and the concentration is also high at the bottom side. So we are going to extract the heat, means the heat exchanger or the pipe which is passing through here to extract the maximum heat. We can pass the heat exchanger pipe here at the bottom side, and that will be passed to the different applications. So one of the application by solar pond, you can recall this. Just finish. So this is just showing the application purpose, required for our syllabus purpose. So here you can observe solar pond is connected to an evaporator, and through this evaporator, any liquid at around 80 to 90 degrees it evaporates. So that liquid we can convert it. Turbine is connected to generator and can generate the electricity like that. Again, we can cool those vapors, condensate with the cooling tower. As like energy systems, we have uh, power plants. Polar cooling tower, from cooling tower, we are going to condensate all the vapor of this liquid, and we can extract the again back to the evaporator. So thing is here what solar pond is acting like a heat exchanger, can absorb maximum heat like a I can give an example.
Javed? Yeah. Sir.
We'll continue the next class, okay, in the next week. Network, some issue is there now. Again. So all of you can leave the meeting. Thank you.